Okay, let's start with the presentation. My name is Mafred Holzer. Thank you for the introduction. Thank you for the invitation to Philip to speak here at this ISPE workshop. I like today to give a high-level presentation on e-beam technology, on the basics of e-beams, on the emitter technology which produce the electrons we need here for the decontamination, on validation, and what is the history behind this technology, and what did we overcome. And some, or actually 2 installed systems in Ireland I'd also like to present in some slides. So it's a bit to do. Let's start. Why do we need e-beam? Basically, e-beam is our transfer technology for pre-sterilized syringes and tubs. They are all decontaminated already in these white boxes with the Tyvek sheet, ethylene oxide sterilized inside and in the bag as well. And then we cut away the bag, and we need to introduce this tub into our isolator in here from a grade C room. So what we do is we transfer the tub here through the e-beams, the emitters, which are here, into the grade A area. And you see we're changing zones from CD over C here, then into grade BA and in the fill grade. This is what we use the e-beam technology for. It's a transfer technology. What options do we have for transfer? We can do it with alcohol, so we just wipe it, but you know it doesn't work against spores and stuff. So the safety is not very high, and it's a batch process. We can do pull slide UV. I know so far only batch processes here, and we have a 3 to 4 log reduction. So again, the safety is not too high. We can use a plasma chamber, also batch-wise working. There we have a 6 log reduction. Then actually there's one installation here, GSK, in UK, in Barnard Castle. They use such a plasma chamber from the company Groninger. And we have H2 airlocks, widely used. Also batch-wise, they give a more than 6 log reduction for this tub to be put in. Then we have the no-touch transfer. This is with a double bag, so you have 2 bags around the tub. Both bags are sterilized, and then you don't touch the tub by putting it through the mouse hole into the isolator. They're usually automatically debagged under a laminar flow grade A. That can be a continuous transfer, but it has a no log reduction on it. And then there's the e-beam. It can have a continuous transfer of up to 6 tubs per minute, means 36,000 syringes per hour. If you use a nest with 160, it's around about 57,000. And the safety, here we have a more than 6 log reduction. Actually, if you look on the spores, it's a 12 log reduction we talk about here. So these are our options, and I'd like to introduce you to the e-beam option. E-beam, how does the system look like? You have the debagger here. Here is your tub, the white part with a Tyvek lid and with the bag around. Automatically, the bag will be cut open and the tub will be transferred into the entry section. This one here is actually the e-beam. Here we have an entry section. Then the tub moves ahead through 3 emitters which surround the tub and which give an electron cloud to decontaminate the surface. And from here it moves into the exit section, into the filling line where it gets delidded and denested, filled, stoppered, renested, and it goes out. From here on it goes back into the room grade C. In the isolator we have the grade A room, and you see the critical point of fill here has the highest pressure. The more we go over here, we have a lower pressure here. At the e-beam here, we have the exhaust. This is how such a system looks like. And when we cut open an e-beam as an example, we see red, the emitters, right here in the middle, doing the decontamination work. We have a conveyor system consisting of 4 independent conveyors. We have shielding. Electrons cause X-rays. X-rays we need to protect the people from. That's why we have shielding. Here are 3 boxes shielded with lead, 6 millimeters of lead, and a couple of doors in front as well. We have an air handling system like in an isolator, H2O2 system, and safety features, of course. If we look on the process, we see there's a tub coming from the debagger. Here is a shutter system moving. Maybe we can switch off the lights. I think it's quite... Or do you see, does everybody see enough? I think it's better. So there's a shutter system moving here, like this. This pretends the X-rays to come out of the system, and the tub is released when the mouse hole is open here, moves towards the emitters here with the electron cloud, and then moves slowly through the electron cloud. All the surfaces of the tub get decontaminated, and once that has happened, it accelerates again into the exit section, into the filling line to be filled. This is what I like to talk about, and I'd like to go now through a bit of the details of the emitters, conveyor system, and these parts, and later on then on references and history on it, to give you a broad overview of this technology. First of all, there are a couple of regulations behind. Important for us is we need to reach a dosimetry of 25 kilogray, a dose of 25 kilogray on the outside of the tub. These 25 kilogray are actually a 12-log reduction of Bacillus pumilus, which is mentioned here in the regulations. This is an industry standard, and it needs to be reached on every position on the outside of the tub. So what is an emitter like, which emits these electrons? An emitter is like a tube. In this tube there is a filament. The filament receives some current, emits electrons, and they get accelerated in an electrical field, go here through a titanium foil onto the object and decontaminate there. An emitter looks in reality, if you cut it open like this, there's a very fine filament here in the middle. Usually the assembly of these critical parts is done by Asian people. They seem to have more patience on that. And then we have an electrical field where we accelerate the electrons, and they go here through a thin titanium foil, 10 micrometer, looks like your aluminium foil you use at home, and go onto the object. This tube is completely under vacuum. Actually, when you look at this is what a tube looks like. And there's a knob on the other side there where they pull vacuum, ultra high vacuum, so that there are no particles and nothing in there, because they would cause shortcuts in this electrical field. And that's hermetically sealed. And here is this window, and there's a support grid underneath, otherwise this small foil would break. And here later on comes the cable, which gives the power, actually the high voltage power to this lamp. So these emitter systems enable us to dose more than 25 kilogray on all tub surfaces on the object we need to decontaminate. They are compact and modular. This lamp is around about this size. It's about 14 kilogram heavy, very easy to handle, and it allows easy integration into our equipment. They have a very high lifetime of more than 6,000 hours. We expect actually more than 8,000 hours. This is important because then you can do preventive maintenance and you can exchange these lamps. Exchange of these lamps is like a light bulb. We can do it immediately after a bit of training. Within 20 minutes we change such a thing. And it doesn't take special skills for that. And it doesn't need field maintenance. This is like a light bulb in here, and really you turn it on and it works. And once a time it dies like a light bulb, and then you need to exchange it. This is when they work. These are the electrons. They come out here, out of the foil, and they are glooming, fluorescing in the air. So what are the properties of these electrons? They have a strong biological kill effect. They kill everything. They don't penetrate deep. They are different to gamma. They only work on the surface. So they only go to a thin layer on the surface. If you say the voltage is responsible for the depth to go in of the electrons, it's around about 0.5 millimeters. So it's really just working on the surface. If somebody's here for medical devices, we can't go inside and decontaminate inside like gamma. That's only working on the top. Then, as I mentioned before, we use voltage. The voltage is responsible for the penetration depth of the dose because the voltage accelerates the electron. The faster the acceleration, the deeper it goes, the further it flies. The current is responsible for the level of the dose. The more current I put on, the more dose I put on, Basically, you can imagine it's like with color. The more I press the can, the more color I get. So the dose on the object surface on the top is a function of the applied voltage. The electron needs to reach the furthest point on the object. It's a function of the current, because here we have the level of the dose. And of course, it's a function of the speed. The exposition time of the object is also very important. We need to know how fast it is, and the slower it moves, the more dose is getting on. Then also important is the emitters. These are free emitters. They are put in a triangle configuration around the tubs we need to decontaminate. Basically, this tunnel here, this conveyor system, can accommodate 2-inch tubs, 3-inch tubs, and 4-inch tubs. We also could build it even bigger. The most used tub size is the 3-inch tub. That's about shoe carton size, around about 120 millimeter high. That's the red one here. The yellow is the 4-inch tub, and that gets decontaminated by these emitters. Shielding is important, as I said before. The electrons, they cause X-ray when they are stopped by other materials or atoms. Everybody remembers physics in school. There's an electron flying in the outer shell of the atom. It hits another electron, gets stopped, Bremsstrahlung, creates X-rays, and this is what we need to prevent the people from. But very important is, if we turn off the system, there's no further production of electrons anymore. So it's not like a nuclear power plant where you, once it is running, where you always have contaminated surfaces. If power is switched off, finish with X-rays, nothing happens. So we have these X-rays, and we need to shield from the X-rays. How do we do this? The electrons are here creating the X-rays, and an X-ray is like a billiard ball. It bumps against the wall somewhere, it goes to the next wall, and so on. If it bumps 3 times against the wall, it has lost all its energy to be harmful for people. So then you can release it to the outside. So what we do is we build a labyrinth for the X-rays. This is how we shield such machines. And therefore, that's actually the free bounce rule that applies. It's 3 bounces and the energy of the X-ray is discharged. So what we do with our E-beam system, we have this parallel shutter shielding system. That's this one, moves up and down, always opens just one mouse hole. And then we have here the creation of the X-ray. So it might go through the first mouse hole, bumps against the shutter, against the wall, and has lost its energy. This looks a bit like this. You see here, conveyor system, the shutter and the tub moves in through the E-beams and then to the outside. Again, what you see in the other picture, yeah. Here it comes now with dosimetry foil on it that gets changing colors, and this was the mouse hole with an automatic seal over there. Okay, so how does the shielding look like? We have, first what we do, we build inside the stainless steel, and then this is lead, 6 millimeter lead, and then we cover everything with the lead. We can even weld the lead, and then we cover again the lead, so that it finally, this corner here, this weld of lead is down here basically, is then covered fully with stainless steel. Also, what we need to do is, we need to make with our authority in Switzerland, we're producing in Switzerland with the SUVA, an appointment, and they approve every E-beam. They measure around the grid here, around the E-beam, and the dose limit is 1 microsievert at 1 hour and 100 millimeters. And they certify each E-beam, and if we deliver it, for example, to Ireland, in Ireland we have 4 E-beam systems, then the authority there comes in, they also do the shielding test, and they release and approve it. Please note, it's a fully protected system. You can lean on the system the whole day while it is working, nothing happens. You do not need to wear dosimeters, and there's no time limit for operators when they're working with an E-beam. It's easy, it's a fully protected device. the tap conveying system. These four are in the E-beam. This is in the entry section with the shutter. This is the left one. Here we have the emitters around. Here we have the gap where we let the electrons go to the tap. And then we have here the exit section going out. And the tap conveying system is very important because it creates maybe particles. This does not. You need to measure the speed and so on. So what we do is the tap in our system is stopped by a conveyor stop. When the tap moves into the entry section, then we switch off the motor. Once it is detected by these two sensors, stopped by a conveyor stop. No rollers grinding on the tap. And then it moves ahead here through the emitter zone and again. Always it's detected by one sensor, so we see on the HMI where is our tap, because we can't view inside here into these sections. We do the speed measurement as a function of time and distance. Basically, when the tap hits the sensor here, we start the measurement. When it leaves with the tail of the sensor here, we stop the measurement and we alarm it. So we monitor the voltage, we monitor the milliamps, we monitor the speed, and then you know it was GMP-wise correct function. Also, we have a jog mode to drive the tap manually forward and backward, and a dosimetry feature for validation. So this is a bit of the life of a tap when it goes through an E-beam. We have a camera in the second tap. First one is now in the entry section. Shutter is moving. And now you see the glooming light of the emitters coming around. You see a bit, if I have my emitter here, I'm shadowing with the tap or with the system itself, the tap, the back. So these are the worst case spots on the tap because they are most far away from the emitters here, and because they are shadowed by the tap itself. So if I release this, you can see it comes around. Now it gets the 25 kilogray. It has it. It accelerates, and the other tap follows with the camera in there. It actually got stuck then because it capsized of the weight in the middle there. Then automatically we switch off the emitters because the emitters generating a bit of heat. We would melt the tap. And now the project manager is driving the tap with the jog mode backward into the entry section. The entry section is not decontaminated with H2O2, and there we can open the door and take it out very easy. So you see here, this is one of the sensors in the bottom, all these red lights. Drives backwards into the entry section. Shutter moves, and you can take out the tap. Very easy if something happens. Air handling system. Also important, we have a unidirectional airflow after the emitter systems here. The emitters are here. And once they are treated, then they are decontaminated. So we supply the right air, which is the grade A air, in this area here. Important is also that here we have the emitters are very close to the exhaust, to exhaust residuals. And also very important is the system can be decontaminated independent or together with the isolator. We have automatic mouse holes, inflatable seals, which inflate against the shutters here and here. This is the entry section here. You see it's not getting decontaminated. And so we have all possibilities to decontaminate. Validation of an E-beam system. IQ, OQ, like on a usual filling line or isolator to be done. Cycle development, microbiological qualification. The tunnel gets decontaminated because you can't decontaminate a tap just on a spot where the emitters are and then let it in the dirty. So you do H2O2 decontamination of the surfaces. And you do the dosimetry to establish the kilograys with a B3 film cord. B3 film comes from Tesa, Bayersdorf in Hamburg, gets also calibrated, and you put the B3 film around the tap to see it. You have seen it before. What is the target of our dosimetry? The target is to have 25 kilogray on all outer surfaces. The dosimetry strategy with the film is, and it's actually 1 week on site, that we have a conveyor speed of, for example, 6 taps per minute, depending on how much you want to fill. That we determine the emitter parameters, the KeV and the milliamps, and the speed. This is from our vendor experience known, so we know that basically. Then we do the dosimetry of the outer surface of the tub and see if we have everywhere achieved the 25 kilogray, which is no issue today. And then we have some residuals in the exhaust and residuals in the tub, which we need to measure. Also, there's a possibility you can do dosimetry with biological indicators, Bacillus pumilus, but that's not mandatory. The 25 kilogray is your measurement. If you achieve the 25 kilogray, you're fine. So how does it look like? We have film dosimeter. These are these ones here. Also like a foil you wrap food in. It's more or less the same. In the beginning, it's clear, and the more dose it gets, the more it changes the color. So the color change is proportional to the applied dose. You can utilize this with a spectrometer or with a scanner and with a special software, and either we can do the service or somebody else can do the service for you or yourself by a bit of a training, also possible. You see here, we put a foil on the top. They are very equal. We get, this should be around about 25, 30 kilogray. And you see here, this is the front of a tub, what we just have seen in the video or the back. In the middle here, we haven't achieved the dose. This is less than 25 on the sides. We have it already because that was closer to the emitters. So the summary is the regulation call for a sterilization dose of 25 kilogray, which will be applied and verified. This is the industry standard, and achieving is no issue at all with today's technology of the emitters, and dosimetry for the validation is sufficient. No BIs unnecessary. So what is an E-beam performance usually doing? If you write a URS, for example, you should write, you will have 6 tubs per minute going through an E-beam system with 25 kilogray on all surfaces on the outside. You expect the high lifetime of the emitter, at least 6,000 and maybe even more, so that it allows for preventive maintenance. Not that you're somewhere in the vaccine business and you're running these things and the emitter goes off and you need to exchange the emitter while your batch is waiting. That's a bit of an annoying part. You need to have easy access for exchange in case. You should be able to exchange it by yourself. There are other emitter suppliers on the market where you need special people. Then you should have an airflow system with unidirectional airflow after the decontamination, integrated H2O2 system, and of course independent or together with the filling line. The conveyor system should be straight, smooth, and a particle-free conveyor system. This is happening here because we have the shutter system, so we don't move the tub around to avoid X-rays coming out. We move the shutter, the shielding. That gives a straight transport, a very short transport, particle-free. We should have a tub position detection, the speed measurement, and the other features like jog mode or dosimetry mode. Only one tub in the emitter zone should be, so you have the freedom to drive backwards if you have an issue and you only lose one tub. Then stainless steel sandwich technology, so you cover all the lead with the stainless around, and no lifting devices necessary to put away the shielding. These doors you have seen, they weigh about 150, 200 kilograms, so they should be hinged, not that you need a forklift truck. A small footprint is good, weight of less than 2 tons per square meter because that's industrialized. Easy and good access for maintenance and cleaning, and all services, including dosimetry, should be done able by the vendor. So a bit of a look into the history. Where did we start with the E-beam technology in the pharmaceutical industry? We started with GSK in Dresden and in Mafred in the year 2000, 2001, and they ordered 4 E-beams at that time from the company Linac that got bought by Lacarlene and then got bought by Gettinger. And GSK decided they needed technology to decontaminate the outside surface of the tub when they transferred into an isolator. I remember we had an isolator with UV light, pulse light. That didn't really work, but this one worked. But you see from the time difference here, the industry was waiting for the FDA approval, for the approval. They finally received it, and 2005 and so on, the other companies also ordered E-beams to get also along with this technology. There was then, up until here, around about 2007-8, where Lynac wasn't in the position to serve anymore all these customers. So the customers got frustrated, they called in, they had issues, nobody could support them. They were asking other people, like Metal and Plastic and Scan, to do their own isolators. And you can see, actually there was one order in 2012, after 2009, 2013. These are the last ones they sold. And then in 2008 and 2009, we started with our e-beam systems, and these companies all here, which I make bold, they changed to the Scan e-beam system, which I just introduced you to. And we started on the top with two in the US, Pfizer in Grange Castle, in Ireland, Merck in Carlow, and Amgen in Dunlager. Then we have Sondo, Novartis, two of them, Sanofi-Le-Tray, Aspen, South Africa, Genzyme in Waterford, and then some in France, Hungary, and another one in Puerto Rico. Actually, these are 13, and I know today, in February, that we have 2 more on order now, so it's 15 e-beam systems. So how many e-beams do we have worldwide in the pharmaceutical industry? It's actually the 21 from Getinge. It's the 13 from Scan plus the 2 we are expecting. 11 has MMP, 5 by Japanese. So we are around about 52 e-beam systems in total for tap transfer worldwide. And these 52 cover more or less 70–80% of the lines with a speed higher than 200. There is no e-beam in front of a line where the speed is not high. You like to do this tap transfer for the high speed lines, for the value products, and And please note, these are only installations, for tap transfer. There are other things as well. You can harden colors with it. For example, if you print t-shirts, you print a t-shirt with an inkjet, and then you harden the color with an e-beam and you can roll it. Otherwise, of course, you would have a mess. Or, as I'm in UK here, the golf ball. The golf ball, the color or the skin of the golf ball is hardened out with e-beam. That's done with e-beam. If you play golf, and check on your golf ball. That's done with e-beam. So there are much more applications, but we just have 52 systems at the moment estimated in the world for tap transfer. After 2008, 2009, there was a time where we had low requirements per year for e-beams. Since the validations of the first ones we delivered, same like GSK in the past there, it's increasing. Basically, at the moment, we have 10, 12 requirements per year for e-beams. Of course, a lot die, a lot will not be realized, but we talk about 4 or 5 more installations per year. So it's kind of a niche technology. I'd like to introduce you to systems installed. So you see here, we have the emitters surrounding the tunnel. That's the emitter itself here. This is the sketch. So we have a room here where the tub comes in, tub gets debagged here, goes through the e-beam, goes into the filling line, delidded, delined in here, then filled, stoppered, and goes out. Actually, here in this system, it goes here on a paternoster system and goes back in the same room. I'll show you the overall layout. So comes in here, paternoster system filled, it gets back, probably because here we have the lift, so all the material is going this way while we have here classified areas. Pictures of this installation, you see here is the debagger, the bag, the tubs in the bag sterilized with ethylene oxide. Then the e-beam here on the side, we have windows made of lead glass to view into the entry and exit section, the isolator behind, and here we see the paternoster system for bringing back the tub. Another system here at Pfizer Grange Castle, we have the debagger in an extra room, in a grade D room, and then we have a grade C room where we have the e-beam, which takes it through a mouse hole through the wall. Then the deliner goes around the corner to the filling line and goes out. Up here we have a rapid transfer airlock, an RTP, and a bit of an in-process workstation for the microbiological people. It's very handy if they can do something in a filling line without stopping the filling line. So it's good to have such a place, either directly on the line, or you have a material transfer isolator offset where you can do all your preparation work. This is the debagging room. This is the E-beam here, the filling line here. This is the other part. And I like this picture very much because we see here the vessel on the scale, and then we have the peristaltic pumps, and here we have the liquid transfer with RTP ports into the isolator. So these are the examples, 2 examples from systems in the pharmaceutical industry. Somebody who you also know very well is using E-beam technology. It's Tetra Pak. Tetra Pak has 2 emitters here and here, and they shoot electrons on their foils from which they form then the brick, the Tetra brick. So that's for milk or for all these other things that can go wrong, can go bad when they have some spores or something in their bacteria. And they also apply the 25 kilogray, and they go with 80 meters per minute. So the foil here is going very rapidly, and you can watch this actually on the internet. So, conclusion on this high-level presentation within this half an hour. You noted I'm on page 128. You only have seen 40 slides. E-beam technology is today very well known. E-beam is the only continuous transfer technology with a 6-log or actually 12-log reduction. The emitter lifetime is no issue anymore. It was an issue in the past. It's buy an emitter from this company and you're happy. It's easy to use and validate, and I can only say it's a no-risk transfer which is required from the FDA. Thank you. I really need to admit it needs a bit longer than half an hour to get all these things through and a bit of example and discussions. Feel free to ask. I'm here until 4 o'clock, then I need to leave. If you ever have a question or you like to have a training on it, I also like to consult and tell you the pros and cons also towards other technologies on this. Feel free to call. Thank you. Any questions? Ah.
Simple, non-commercial question. What do you do in the area of offload from the emitters? Grade A conditions? How do you...
Yes, after the emitters is grade A. Particle counting. Some 30% of the customers do remote viable air sampling in the exit section, but some of them have deinstalled it. So today it's really only particle counting. It's in the exit section it's grade A true. In the tunnel it's a bit but it's clean area from the isolator. It's the same like on the no-touch transfer. Yes, please.
You say that no BI, no biological indicator is needed.
Yes.
How did you establish?
What we did a study where we put Bacillus pumilus inoculated on the tub surface itself. The tub is made of polystyrol. The top is made of Tyvek. We inoculated on it, and then we run this on certain levels of kilogray through it. And we found with 15 kilogray you kill already everything, which is kind of in line because Bacillus pumilus has a D value of 2 kilogray. And as you do the 25, you're really overkilling everything.
But the regulators accepted that?
The regulators accept the 25. Okay. With this system, you're finished within 3 days with the validation work on the dosimetry side. It's very easy. You just need to go around your tub with the foil, which is really like a foil you have in the kitchen as well, and then you decontaminate it and you measure the dose on it by changing the color and with a certain software. There's a Reso lab called in Denmark. They are specialized in this. They give training. They have issued a guidance to do this. They do also calibration of these films and stuff, and they are very handy to talk to and to work with. Very easy. Can give you advice on that, address, etc. Okay. Thank you.